A gram of gold costs $160. A gram of something else? $62 trillion? You'll discover what makes certain substances worth more than entire countries. I'm just as curious as you are. Let's start with something that feels like sci-fi: antimatter. The mirror opposite of everything around you. While you weigh maybe 70 kilograms, if you were made of antimatter and shook hands with your regular matter self, both of you would vanish in an explosion that would vaporize a city. It's real. It's the most expensive substance on Earth, and it costs $62.5 trillion per gram. But here's the twist. Nobody's getting rich selling antimatter. There's no antimatter market. The price tag isn't what someone paid. It's what it costs to make. And that cost is absolutely astronomical. To create antimatter, scientists at CERN, the European Organization for Nuclear Research, built the Large Hadron Collider. This machine is 10 miles in circumference, contains 9 300 supercooled magnets, and consumes enough electricity to power a large city. The construction alone cost $4.75 billion. Operating it costs another billion per year, with electricity bills running $23.5 million annually. Here's the reality. With current technology, it would take 100 billion years to produce just 1 gram of antihydrogen. That's 7,000 times longer than the universe has existed. Even if you ran the collider continuously, the total amount of antimatter humanity has ever produced wouldn't power a light bulb for more than a few seconds. So why does it matter? Because when matter meets antimatter, they annihilate each other, converting 100% of their mass directly into energy, according to Einstein's E=mc². This is millions of times more efficient than nuclear reactions. Theoretically, 1 gram of antimatter could power a spacecraft to Mars in just 1 month, instead of the current 9-month journey. But we're not even close. Antimatter represents the absolute ceiling of expense, a substance so costly to produce that it exists more as a theoretical possibility than a practical reality. Now let's drop down several $1,000 trillion and talk about something you can actually buy. The second most expensive substance on Earth is something that looks like salt: white powder. Completely unimpressive to look at, but it sells for $140 to $167 million per gram. It's called nitrogen atom-based endohedral fullerenes. Let's break that down because the name is ridiculous, but the science is beautiful. Imagine 60 carbon atoms arranged in a perfect sphere, like a miniature soccer ball. That's called a buckyball, named after architect Buckminster Fuller, who designed geodesic domes with the same geometric pattern. Now trap a single nitrogen atom inside that cage. That's an endohedral fullerene. A company at Oxford University called Designer Carbon Materials is the only place in the world that makes these. They recently sold 200 micrograms. That's about 1/3 the weight of a single human hair for $33,400. Scale that up, and you get about $167 million per gram. Why so expensive? 2 reasons. First, they're incredibly difficult to manufacture. The company can produce high-quality material at only 50 milligrams per day, and it takes weeks to purify each batch. Second, demand is growing because these molecules could revolutionize timekeeping. Atomic clocks are currently the size of entire rooms. They're essential for GPS systems, keeping time so precisely that GPS can pinpoint your location. But these clocks are massive and power-hungry. Endohedral fullerenes could shrink atomic clocks down to microchip size, small enough to fit in your smartphone. Imagine GPS accurate to within 1 millimeter instead of several meters. Imagine autonomous vehicles knowing their exact position, even in tunnels where GPS signals are weak. That's the promise. That's why investors and researchers are willing to pay $167 million per gram for this white powder. Let's keep descending the price ladder. We're now at $27 million per gram. Californium-252, an element that doesn't exist anywhere in nature. It has to be manufactured atom by atom in nuclear reactors by bombarding plutonium-239 with neutrons. The process takes almost 2 years from start to finish, and only 2 facilities in the entire world can do it: Oak Ridge National Laboratory in Tennessee and the Research Institute of Atomic Reactors in Russia. Combined, they produce less than 1 gram per year. The element itself is silvery white, highly radioactive, and has a half-life of just 2.6 years, meaning half of it decays to other elements within that time. This short half-life means you can't stockpile californium. It has to be continuously produced. But here's what makes it valuable. Californium-252 is a neutron bomb in miniature. A single microgram, 1/1,000,000th of a gram emits 170 million neutrons per minute. Those neutrons can start nuclear reactions, detect oil deposits deep underground, help treat certain cancers, and even detect explosives and weapons at security checkpoints. The military uses it. The oil industry uses it. Cancer treatment centers use it. And because supply is so limited and production is so expensive, the price stays locked at about $27 million per gram. Now here's where things get really interesting. We shift from manufactured elements to something that nature makes but refuses to make much of. Red diamonds. Diamonds themselves are rare. Colored diamonds are rarer. But red diamonds? They're so rare that only 20 to 30 true red diamonds are known to exist in the world. Most are smaller than half a carat. The largest red diamond ever found, the Priciest red, weighs just 5.11 carats. It was discovered in Brazil in the 1990s as a rough stone weighing 13.9 carats. After careful cutting, it became a triangular, brilliant cut stone that sold for over $20 million. That works out to about $1 million per carat, or $5 million per gram. Here's the odd thing. Scientists still don't fully understand what makes red diamonds red. Most colored diamonds get their color from impurities. Nitrogen atoms make diamonds yellow. Boron makes them blue, but red diamonds are pure carbon. The current theory is that during their formation, extreme pressure caused plastic deformation in the crystal lattice structure, bending the molecular bonds in ways that absorb certain wavelengths of light. The result? Red. The Argyle mine in Western Australia was the world's primary source of red and pink diamonds. When it closed in 2020, the supply essentially evaporated. Since then, red diamond prices have exploded. A 1.21 carat fancy orangey red diamond sold at auction in 2023 for $1.76 million. That's $1.45 million per carat. These aren't stones anyone wears. They're investment assets, purchased by collectors and kept in vaults. They appreciate faster than almost any other tangible asset on Earth. Right behind red diamonds come their blue cousins. Blue diamonds at approximately $10 to $15 million per gram for top specimens. Blue diamonds are extraordinarily rare. Less than 0.02% of all mined diamonds show blue color. They come from only a handful of mines worldwide, primarily the Cullinan mine in South Africa, and historically from the Argyle mine in Australia. The most expensive blue diamond ever sold is the Blue Moon of Josephine, a 12.03 carat fancy vivid blue diamond that fetched $48.5 million in 2015. That's just over $4 million per carat. The stone was discovered in South Africa's Cullinan mine in 2014 as a 29.62 carat rough stone and cut down to achieve perfect clarity and color. The price per gram for blue diamonds varies dramatically based on color intensity. A medium-toned 1-carat blue diamond averages $200,000, but fancy, vivid blue diamonds, the deepest, most saturated blues, can command $2 to $3 million per carat at major auctions. That translates to $10 to $15 million per gram. What makes this particularly fascinating is that blue diamonds are actually type IIB diamonds, meaning they contain so little nitrogen that they're extremely pure. They're not just beautiful, they're also electrical conductors, unlike regular diamonds. That boron doesn't just add color, it fundamentally changes the diamond's physical properties. Let's talk about something completely different, but equally strange. Moon dust. Lunar regolith, to be technical, the powdery gray soil covering the moon's surface. Estimated at approximately $4 million per gram for authenticated Apollo samples. NASA values authenticated Apollo mission lunar samples at hundreds of thousands of dollars per gram. A few years ago, a bag containing trace amounts of moon dust used by Neil Armstrong sold at auction for $1.8 million. The bag itself weighed almost nothing. What sold was the history and the infinitesimal particles of lunar material inside. Here's the catch. It's illegal for private citizens to own moon rocks collected by NASA. They belong to the United States government and are held in trust for humanity. The samples used in research are carefully tracked and must be returned. But a few items, like that contaminated bag, have slipped through legal loopholes and become available at auction. Why so expensive? Scarcity. Between 1969 and 1972, the 6 Apollo missions that landed on the moon brought back a total of 382 kilograms, about 842 pounds, of lunar material. That's it. That's all the moon dust humanity has ever collected from the surface. And most of it sits locked in the Lunar Sample Laboratory facility at Johnson Space Center in Houston, reserved for scientific study. What makes lunar regolith scientifically valuable is what it tells us about the moon's history. The material has been bombarded by solar wind and cosmic rays for billions of years. It contains isotopes and compounds that don't exist on Earth. By studying these samples, scientists can understand the moon's formation, the history of the solar system, and even test theories about how planets form. The irony? The moon's surface is covered in this stuff, an estimated 12 meters deep on average. There are trillions of tons of it. But because only a few hundred kilograms have been brought to Earth, each gram is worth millions. Now we enter the realm of rare gemstones, substances that nature creates through geological accidents, so improbable they happen only a handful of times in history. Painite at approximately $250,000 to $300,000 per gram, $50,000 to $60,000 per carat for top specimens. Until 2001, only 3 painite crystals were known to exist in the entire world. 3. That's not a typo. The first painite was discovered in Myanmar in the 1950s by British mineralogist Arthur C.D. Payne, who initially thought it was a ruby. When analysis proved it was an entirely new mineral, it was named after him. For nearly 50 years, painite held the Guinness World Record as the rarest gemstone on Earth. Then, in 2002, new deposits were discovered in northern Myanmar. Suddenly, instead of 3 crystals, there were hundreds. But here's the crucial detail. Most of this material is too dark, too heavily included, or too fragmented to be faceted into gems. Gem-quality painite remains extraordinarily rare. Painite is a borate mineral containing calcium, zirconium, boron, aluminum, and oxygen. Its deep red to brownish red color comes from trace amounts of chromium and vanadium. The color intensity depends on these trace elements, and stones with rich, saturated color are the most valuable. As of 2025, gem-quality painite exceeds $60,000 per carat. That's $300,000 per gram. Only about 1,000 specimens are known worldwide, and the vast majority reside in museum collections or are held by serious gemstone collectors. You won't find painite jewelry in any retail store. Each stone is essentially a museum piece that happens to be privately owned. What's fascinating is that painite forms in metamorphic rocks called skarns, coarse-grained stones filled with minerals containing calcium, iron, and magnesium. These form only under very specific temperature and pressure conditions. Myanmar remains the only significant source, and even there, finding painite requires processing tons of material to recover a single crystal. Curium-244 at approximately $185,000 per gram. Named after Marie and Pierre Curie, curium doesn't exist in nature, at least not in any measurable quantity. It has to be created in nuclear reactors by bombarding plutonium or americium with neutrons. The process is complex, dangerous, and phenomenally expensive. NASA uses curium-244 and radioisotope thermoelectric generators, RTGs, to power space probes. When missions go beyond Mars, where solar panels become ineffective, RTGs provide electricity by converting radioactive decay heat into power. The Curiosity rover on Mars is powered partly by curium-based RTGs. The cost, around $185,000 per gram, reflects the difficulty of production, the specialized facilities required, and the extremely limited supply. Only a handful of labs worldwide can produce curium-244, and production is measured in grams per year, not kilograms. Musgravite at approximately $175,000 per gram, $35,000 per carat for top specimens, with exceptional stones reaching $40,000 to $50,000 per carat. Musgravite is so rare that between its discovery in 1967 and 2005, only 8 gem-quality stones had been found. 8 stones in 38 years. Discovered in the Musgrave Ranges of South Australia, musgravite belongs to the tophiite mineral family. It's a beryllium aluminum oxide that forms only under extremely specific geological conditions. The color ranges from translucent olive green to grayish purple, with violet specimens being the most prized. What makes musgravite particularly frustrating for gemologists is that it looks nearly identical to tophiite. The only way to distinguish them is through advanced spectroscopy, specifically Raman spectroscopy or X-ray diffraction. Their physical and optical properties are so similar that many supposed Ta-Apheites in museums have later been re-identified as musgravite, and vice versa. Musgravite has been found in tiny quantities in Sri Lanka, Madagascar, Greenland, and Tanzania, but Australia remains the primary source. Even there, most material is non-gem quality. The largest known muscovite, called the Ophir Grand Muscovite, weighs 214 carats, but most faceted stones are under 2 carats. With a hardness of 8 to 8.5 on the Mohs scale, muscovite is durable enough for jewelry, but you'll never see it in a retail store. When gem-quality muscovite appears at auction, it routinely fetches $30,000 to $35,000 per carat, with exceptional specimens exceeding that. Collectors treat these stones as investments, not ornaments. Grandidorite at approximately $105,000 per gram, around $20,000 to $21,000 per carat. First discovered in Madagascar in 1902, grandidorite was named after French explorer Alfred Grandidier. For over a century, it remained essentially a collector's curiosity, known to exist but almost never found in gem quality. The breakthrough came in the early 2000s when new deposits were found in southern Madagascar. Suddenly, tiny amounts of transparent grandidierite became available. But even with these new finds, gem-quality material remains extraordinarily scarce. Grandidierite is a borosilicate mineral with a stunning blue-green color. What makes it particularly special is its strong trichroism. When you look at the stone from different angles, it shows 3 distinct colors: dark blue-green, colorless, and dark green. This optical effect is dramatic and mesmerizing. Most grandidierite is translucent to opaque and suitable only for cabochons. Transparent, faceable material is the exception, not the rule. Stones over 1 carat with good transparency are incredibly rare, and those command the highest prices. The price per carat varies dramatically based on transparency and size. Lower-grade translucent material might sell for a few $100s per carat. The transparent, well-cut grandidierite routinely fetches $20,000 to $21,000 per carat, about $105,000 per gram. Interestingly, Madagascar is essentially the only source. A few specimens have been found in Sri Lanka and Malawi, but these are rare even by grandidierite's standards. The gemstone forms in metamorphic rocks under very specific conditions, and those conditions are apparently unique to a small region of southern Madagascar. Tophiite at approximately $100,000 per gram, around $20,000 per carat. Tophiite has one of the strangest discovery stories in gemology. In 1945, gemologist Richard Taff was sorting through a box of spinels in Dublin when one stone didn't look quite right. He sent it for analysis and discovered it was an entirely unknown mineral. This is remarkable because tophiite was the first gemstone to be identified from a cut and polished stone rather than from a rough crystal. Someone had mined it, cut it, sold it, and it had been traded as a spinel for years before anyone realized it was something completely different. Tophiite is a beryllium magnesium aluminum oxide. It forms in metamorphic limestones and has been found primarily in Sri Lanka and Tanzania, with minor occurrences in China and Myanmar. But even in these sources, it's incredibly rare. Estimates suggest that for every million gemstones mined, one might be tophiite. The color ranges from colorless to mauve, violet, red, or brown. Pale lavender stones are particularly prized. Like muscovite, its close relative, tophaite is often mistaken for spinel or even sapphire. Only laboratory testing can confirm its identity. Gem-quality tophaite typically sells for around $20,000 per carat, or $100,000 per gram. Larger stones command premium prices because they're even rarer than small ones. A 2-carat tophaite is not twice as valuable as a 1-carat stone. It's exponentially more valuable because finding one is exponentially less likely. Most faceted tophaites are under 1 carat. Stones over 2 carats are museum-quality rarities. Collectors who own them guard them carefully, knowing they possess something that exists in only tiny quantities worldwide. Now we shift to a very different category of expensive substances: illegal drugs. LSD, lysergic acid diethylamide, at approximately $75,000 per gram. This price seems absurd until you understand the dosing. A typical recreational dose of LSD is 100 to 200 micrograms. That's millionths of a gram, which means 1 gram of pure LSD contains 5,000 to 10,000 doses. LSD is usually sold by the dose, typically $5 to $15 per tab on the street. But if you scale that up to pure gram pricing, you get into the tens of thousands per gram. The $75,000 figure represents high-purity laboratory-grade material or theoretical street value. The synthesis of LSD is complex and requires advanced chemistry knowledge. The precursor molecule, lysergic acid, is derived from ergot fungus. which grows on rye and other grains. The synthesis involves multiple steps, specialized equipment, and dangerous reagents. Only sophisticated laboratories can produce it. What makes LSD particularly expensive in pure form is that very few people ever handle it that way. It's almost always diluted onto blotter paper, sugar cubes, or liquid. A gram of pure LSD would represent an enormous quantity, enough to supply thousands of users. Law enforcement rarely encounters it in this form. The high per gram price reflects both the complexity of manufacture and the compounding of markup at each distribution level. From chemist to distributor to dealer to user, the price increases at each step. By the time it reaches end users as individual doses, the effective per gram price is astronomical, even though each dose costs relatively little. Red Beryl, sometimes called Red Emerald or Bixbite, at approximately $50,000 per gram, $10,000 per carat. Red Beryl is found in only one place on Earth where gem-quality crystals occur, the Wawa Mountains of southwestern Utah. That's it, one mountain range in one state. This gemstone forms in volcanic rhyolite, created when beryllium, aluminum, silicon, and oxygen crystallize in cavities left by gas bubbles in cooling lava. The red color comes from trace amounts of manganese. The conditions required for red beryl formation are so specific that even within the Wawa Mountains, only tiny pockets contain it. The mine that produced most gem-quality red beryl, the Violet claims, was exhausted and closed permanently. New material occasionally appears from old stockpiles or minor discoveries, but the supply is essentially fixed. What exists now is all that will ever exist from that source. Most red beryl crystals are tiny, under 5 millimeters. Face-stable material over 1 carat is extraordinarily rare. The largest known faceted red beryl is only about 8 carats. Compare this to emeralds, where 50-carat stones exist. Red beryl simply doesn't form in large crystals. The price, typically $10,000 per carat, or $50,000 per gram, reflects this severe size limitation and single-source supply. When the Violet claims mine closed, the available supply became fixed. Demand hasn't decreased, but supply can only shrink as collectors buy up existing stones. Red beryl is harder than emerald, 7.5 to 8 on the Mohs scale, and has better clarity, but its value comes entirely from rarity. If large deposits were discovered tomorrow in another location, prices would crater, but geologically, that seems unlikely. The conditions that created red beryl in Utah were a one-time accident of volcanic activity, mineral chemistry, and timing. Helium-3 at approximately $37,000 per gram, though prices vary dramatically. Helium-3 is an isotope of helium with one less neutron than regular helium-4. On Earth, it's extraordinarily rare, existing only in trace amounts in the atmosphere and as a decay product of tritium. Most of the helium-3 available today comes from nuclear weapons. Tritium, a component of thermonuclear warheads, decays with a half-life of 12.3 years into helium-3. The United States and Russia produce helium-3 as a byproduct of maintaining their nuclear arsenals. After September 11, 2001, demand for helium-3 spiked because it's used in neutron detectors for screening cargo at borders. These detectors can spot smuggled nuclear materials. Medical imaging also uses helium-3 for specialized lung scans, and quantum computing researchers need it for dilution refrigerators that cool systems to near absolute zero. Prices have been volatile. In 2008, helium-3 sold for about $100 per liter. By 2010, shortages drove prices to $2,000 per liter, about $15,000 per gram at helium-3's low density. Current estimates range from $2,000 to $15,000 per liter, depending on purity and source, translating to roughly $37,000 per gram at the high end. The ironic twist? The moon is covered in helium-3. Billions of years of solar wind bombardment have embedded helium-3 atoms into lunar regolith. Some estimates suggest there are 1 million tons of helium-3 on the moon's surface. Companies like Interloon are now developing plans to mine it. If helium-3 fusion reactors ever become practical, the demand would skyrocket. A single fusion plant might need 100 kilograms per year. At current prices and supply, that's impossible. Lunar mining might be humanity's only option for scaling up helium-3 supply. Tritium at approximately $30,000 per gram. Tritium is hydrogen's radioactive cousin, 1 proton plus 2 neutrons instead of hydrogen's usual single proton. It doesn't exist naturally on Earth in significant quantities. The small amount in the atmosphere comes from cosmic ray interactions, but that's negligible. All commercially available tritium is manufactured in nuclear reactors, primarily heavy water reactors like Canada's CANDU or Canada Deuterium Uranium design. These reactors use deuterium, heavy water, as a moderator, and neutron bombardment of deuterium occasionally produces tritium. Canada's Darlington Tritium Recovery Facility extracts about 2.5 kilograms per year from the heavy water moderator. That's essentially the global supply from this source. Additional tritium comes from the United States nuclear weapons program, but that supply is declining as the nuclear arsenal shrinks. Tritium has a half-life of 12.3 years, meaning half of any stockpile decays away in that time. You can't store tritium indefinitely. It must be continuously produced. What makes tritium valuable? Its applications are diverse. Exit signs and watch dials use tritium's radioactive glow. No batteries needed. They glow continuously for 10 to 20 years. Fusion research relies on tritium as fuel for deuterium-tritium reactions, the easiest fusion reaction to achieve. And tritium tracers are used in medical and environmental research. The price, around $30,000 per gram, is expected to rise dramatically. Some projections suggest tritium could cost $100,000 to $200,000 per gram by mid-century, as nuclear weapons stockpiles age and fewer reactors produce it. For fusion energy to become practical, scientists must solve the tritium breeding problem, using fusion reactions themselves to create more tritium than they consume. Right now, the world's entire commercial tritium supply is measured in kilograms. A single large fusion power plant would need hundreds of kilograms per year. The math doesn't work yet. That's why tritium remains both expensive and strategically critical. Solaris eculizumab, at approximately $21,000 per gram. Solaris isn't a substance you mine or manufacture in conventional ways. It's a monoclonal antibody drug used to treat extremely rare blood disorders, like paroxysmal nocturnal hemoglobinuria, PNH, and atypical hemolytic uremic syndrome, AHUS. Patients with these conditions lack certain proteins that regulate the immune system's complement cascade, a part of immune response that destroys cells. Without regulation, the complement system attacks the patient's own red blood cells, leading to anemia, organ damage, and potentially death. Solaris works by blocking a specific component of the complement system, C5 protein, preventing it from initiating cell destruction. For patients with PNH or AHUS, this drug is literally life-saving. Before Solaris existed, PNH had a median survival of 10 to 15 years after diagnosis. With Solaris, many patients live normal lifespans, but the drug is astonishingly expensive. Annual treatment costs approximately $500,000 to $700,000 per patient in the United States. Patients typically need infusions every 2 weeks for life. A typical dose is 900 to 200 milligrams, delivered intravenously. The high cost reflects the drug's development expenses, the small patient population, only a few thousand worldwide, and the complexity of manufacturing monoclonal antibodies. Solaris is produced using Chinese hamster ovary cells that have been genetically engineered to produce the antibody. The production process requires sophisticated bioreactors, purification systems, and quality control. When you calculate the price per gram, roughly $21,000, it places Solaris among the world's most expensive substances. But unlike gemstones or rare elements, Solaris saves lives. The cost-benefit calculation is entirely different. How much is a year of life worth? How much is preventing organ failure worth? Insurance companies and healthcare systems struggle with this question. Some countries' health services cover Solaris completely. Others negotiate price reductions. The United States generally leaves patients and insurers to negotiate individually, resulting in the highest prices globally. Benituite at approximately $20,000 per gram, $4,000 per carat. Benituite is California's state gemstone, and it's found in gem quality in essentially one place, a single mine in San Benito County, California. That mine, the Dallas Gem Mine, was exhausted and closed in 2006. Benitoite forms in serpentinite rocks under specific temperature and pressure conditions found only in that location. The mineral is barium titanium silicate, and its brilliant blue color comes from titanium. Under ultraviolet light, benitoite fluoresces bright blue-white, making it easy to identify. What makes benitoite particularly striking is its dispersion, its ability to split white light into spectral colors. Benitoite's dispersion exceeds that of diamond, meaning properly cut stones show incredible fire. When light hits a well-cut benitoite, you see flashes of color rivaling or exceeding what you'd see in a diamond. The problem is size. Most benitoite crystals are tiny, under 1 carat when faceted. Finding a benitoite over 2 carats is rare. Stones over 5 carats are museum pieces. The largest faceted benitoite is only about 15 carats. Since the Dallas gem mine closed, the supply has been fixed. No new benitoite is being mined. Prices have risen steadily. High-quality stones now sell for around $4,000 per carat, about $20,000 per gram. Exceptional specimens command even higher prices. Small amounts of benitoite have been found in Japan and Arkansas, but these occurrences produce mainly specimens for mineral collectors, not faceable gems. California's San Benito deposit remains unique. Scorpion venom at approximately $10,000 per gram, though this varies wildly. The Deathstalker scorpion produces one of the most valuable animal-derived substances on Earth. Its venom contains proteins and peptides that researchers are studying for potential treatments of brain tumors, diabetes, and autoimmune diseases. But extracting scorpion venom is absurdly difficult. Each scorpion produces only tiny amounts, typically 2 milligrams per milking session. You'd need to milk 500 scorpions to get 1 gram. And you can't just grab a scorpion and squeeze it. The process involves carefully restraining the animal and applying mild electrical stimulation to trigger venom release. The scorpions must be kept alive and healthy. They're dangerous. Deathstalker venom can be lethal to humans, especially children or people with health issues. Workers must use extreme caution, and scorpions can only be milked every few weeks, allowing time for venom regeneration. The $10,000 per gram price tag reflects this labor-intensive process, the danger involved, and the specialized knowledge required. But pharmaceutical researchers pay willingly because the venom contains unique molecules not found elsewhere in nature. Specific components of Deathstalker venom, like chlorotoxin, can bind to brain tumor cells. Researchers are developing diagnostic tools that use fluorescent markers attached to chlorotoxin to help surgeons see tumor boundaries during operations. This could dramatically improve brain surgery outcomes. Other scorpion species produce valuable venoms too, but prices vary enormously by species, purity, and intended use. Medical research-grade venom commands premium prices. Lower-grade material for anti-venom production sells for much less. Plutonium-238 at approximately $8,000 per gram. Plutonium-238 is a radioactive isotope that doesn't exist in nature and must be manufactured in nuclear reactors. Unlike plutonium-239, the isotope used in nuclear weapons, plutonium-238 isn't useful for bombs. Its half-life is too short, 87.7 years, and it emits the wrong type of radiation. But that wrong radiation makes it perfect for power generation in space. Plutonium-238 undergoes alpha decay, releasing helium nuclei that convert to heat. This heat can be converted to electricity using thermoelectric materials. NASA's deep space missions rely on radioisotope thermoelectric generators, or RTGs, is powered by plutonium-238. The Voyager probes, now beyond the solar system, are still transmitting data 47 years after launch using plutonium-238 RTGs. The Curiosity and Perseverance rovers on Mars use them. New Horizons, which flew past Pluto, uses one. The problem? The United States stopped producing plutonium-238 in 1988. For decades, NASA relied on stockpiled material and purchases from Russia. That stockpile dwindled. By the early 2010s, concerns grew that future missions might be impossible. In 2013, Oak Ridge National Laboratory restarted plutonium-238 production, but the process is slow and expensive. They produce about 300 to 500 grams per year at full capacity. Each gram costs approximately $8,000 to produce, not including decades of infrastructure investment. The high cost reflects the complexity of production, the specialized facilities required, and the limited supply. You can't simply order plutonium-238 online. It's tightly controlled, exists only in government facilities, and is reserved for critical missions where solar panels won't work. As space exploration pushes deeper into the solar system and plans develop for missions beyond, plutonium-238 demand will increase. NASA is exploring alternatives, more efficient thermoelectrics, nuclear fission reactors, or other power sources. But for now, plutonium-238 remains the gold standard for deep space power. Plutonium-239 at approximately $6.500 per gram. Unlike plutonium-238, plutonium-239 is infamous. This is the isotope used in nuclear weapons and in nuclear reactors. It has a half-life of 100 years and undergoes fission when struck by neutrons, the basis of nuclear chain reactions. Plutonium-239 doesn't exist in nature either. It's created in nuclear reactors when uranium-238 captures a neutron, becomes uranium-239, and through 2 beta decays, transforms into plutonium-239. Military plutonium production happens in specially designed reactors, optimized to maximize plutonium-239, while minimizing contamination from other plutonium isotopes. Civilian nuclear power plants also produce plutonium-239 as a byproduct, though in mixtures less suitable for weapons. The price, around $6.5 per gram, is somewhat theoretical, because plutonium-239 isn't traded on an open market. It's strictly controlled under international treaties. The figure represents estimated production costs and black market values in cases where plutonium has been illicitly trafficked. A nuclear weapon requires several kilograms of plutonium-239. At $6.5 per gram, that's tens of millions of dollars just for the plutonium, not counting weapon design, engineering, testing, and delivery systems. The expense serves as a partial barrier to nuclear proliferation. Countries or groups seeking nuclear weapons face enormous costs and technical challenges. Producing weapons-grade plutonium requires operating reactors specifically for that purpose, reprocessing facilities to separate plutonium from spent fuel, and sophisticated handling systems. International inspectors work to detect and prevent undeclared plutonium production. The Nuclear Non-Proliferation Treaty restricts who can possess plutonium, and physical security measures guard existing stockpiles. Yet despite all this, several thousand tons of plutonium exist globally, enough to build tens of thousands of weapons. The high value of plutonium-239 reflects both its production difficulty and its dual-use nature. The same material that powers reactors can destroy cities. That combination makes it one of the most carefully controlled substances on Earth. Snake venom at approximately $4,000 per gram, though this varies wildly by species and purity. Like scorpion venom, snake venom has legitimate medical applications. Enzymes and proteins in various snake venoms are used to develop antivenoms, study blood clotting, and investigate neurological processes. King cobra venom, Russell's viper venom, black mamba venom, each contains different compounds with different applications. Some venoms have anticoagulant properties, preventing blood clotting. Others are procoagulants causing rapid clotting. Neurotoxins affect the nervous system, while hemotoxins destroy tissue and red blood cells. Extraction is similar to scorpion milking, but adapted for snakes. Handlers use specialized equipment to coax snakes into biting through a membrane stretched over a collection container. The venom drips into the container and is then freeze-dried for storage. Each snake produces different amounts. A large king cobra might yield 500 milligrams per milking. A smaller species might produce only 50 milligrams. Snakes can't be milked frequently. They need weeks to regenerate venom. The danger is obvious. A single mistake can result in a potentially fatal bite. Snake venom extraction requires trained professionals with anti-venom immediately available. Facilities must meet strict safety standards. Prices range from hundreds to thousands of dollars per gram depending on the species. Rare species with medically interesting properties command premium prices. The $4,000 per gram figure represents high-end pricing for particularly valuable venoms. Research applications include developing new antivenoms, studying drug delivery mechanisms, and investigating targeted cancer treatments. Some venom components can selectively bind to tumor cells, making them potential vectors for delivering chemotherapy directly to cancer while sparing healthy tissue. Heroin at approximately $250 per gram street price, though this varies dramatically by location, purity, and date. Heroin, diacetylmorphine, is synthesized from morphine, which is extracted from opium poppies. The chemistry isn't particularly complex, but legal restrictions, law enforcement pressure, and distribution networks create the value chain. Wholesale prices vary enormously. In Afghanistan or Myanmar, major production regions, bulk heroin might cost $3,000 to $5,000 per kilogram, $3 to $5 per gram. By the time it reaches European or American street markets after multiple distribution levels, prices can reach $100 to $300 per gram or higher, depending on purity. The $250 per gram figure represents typical street pricing in many Western markets, but purity varies wildly. Street heroin is often cut with other substances, from relatively harmless fillers like lactose to dangerous additives like fentanyl. Actual heroin content might be 20% to 60%, meaning the effective price per gram of pure heroin is much higher. What makes heroin expensive isn't production cost. The chemistry is straightforward and raw materials are cheap. The cost comes from illegality, smuggling risks, law enforcement losses, danger payments at each distribution level, and the premium charged for an illegal product with inelastic demand. From a public health perspective, heroin's high price creates perverse incentives. Users commit crimes to fund addiction. Dealers face violence from competitors. The illegal market concentrates wealth in criminal organizations. Many economists and public health experts argue that the costs of prohibition, crime, incarceration, health impacts, exceed the costs of regulated legal distribution with treatment programs. But unlike previous substances on this list, heroin's value comes entirely from its addiction potential and illegal status. There's no inherent scarcity. Opium poppies grow readily in many climates. The chemistry is simple. If legal, heroin might cost a few dollars per gram to produce. Prohibition creates the price. Cocaine at approximately $200 per gram street price, with similar caveats to heroin. Cocaine is extracted from coca leaves, which grow primarily in Colombia, Peru, and Bolivia. The coca plant has been used for centuries by indigenous peoples in the Andes for its mild stimulant effects. Chewing coca leaves provides a slight energy boost, similar to strong tea. But extracting and purifying cocaine from coca leaves requires chemical processing. Leaves are soaked in solvents, processed with acids and bases, and refined into cocaine hydrochloride, a white powder. Like heroin, cocaine's price structure reflects its illegal status. Wholesale prices in production regions might be $2,000 to $4,000 per kilogram, $2 to $4 per gram. By the time it reaches retail markets in the United States or Europe, prices typically range from $80 to $200 per gram, depending on location, purity, and local market dynamics. Street cocaine is often heavily cut. Pure cocaine would be dangerous to use recreationally. Users have adapted to diluted products. Common cutting agents include lidocaine, benzocaine, caffeine, levomazole, and simple inert powders. Actual cocaine content varies from 20% to 80%. Testing is the only way to know. The $200 per gram street price represents typical retail pricing in many Western markets, but purity variations mean the effective price per gram of pure cocaine is higher. Like heroin, cocaine's value comes primarily from prohibition. The coca plant could be grown commercially. Extraction and purification aren't particularly difficult. If legal, pure cocaine might cost $5 to $10 per gram to produce and distribute. Illegality multiplies that by 20 to 40 times. And finally, we come full circle to where we started. Gold at approximately $164 per gram, $120 per troy ounce at recent pricing. Gold sits at the bottom of this list, the least expensive substance we've discussed. Yet gold is the reference point against which all others are measured. Gold is valuable for fascinating reasons. It's rare enough to be precious, but common enough to have practical applications. It doesn't corrode or tarnish. Gold jewelry buried for thousands of years emerges unchanged. It's malleable and ductile. You can hammer gold into sheets so thin they're translucent, or draw it into wires finer than human hair. Gold conducts electricity excellently and resists corrosion, making it ideal for electronics. Every smartphone contains a tiny amount of gold in its circuitry. Gold reflects infrared radiation, so it's used in spacesuits and satellite components. Gold compounds treat rheumatoid arthritis. But gold's primary value is cultural and financial. For millennia, humans have assigned value to gold. It serves as a store of value, a medium of exchange, and a hedge against inflation. When currencies fluctuate, investors buy gold. When markets crash, people flee to gold. Unlike antimatter, gold actually exists in tradable quantities. Unlike endohedral fullerenes or californium-252, you can buy and sell gold anywhere in the world instantly. Unlike rare gemstones, gold's value is liquid and universally recognized. That's the paradox of this entire list. The most expensive substances are often the least useful to ordinary people. You can't easily buy them, sell them, or use them. Their value exists in theoretical spaces, scientific research, deep space exploration, museum collections, specialized medicine. Gold, by comparison, is practical, stable, accessible. You can walk into a store and buy a gold coin. You can sell it anywhere, anytime. Banks hold gold reserves. investors include it in portfolios. Sometimes, the least expensive item on the list is the most valuable. Let's pause here and recognize something crucial about everything we've discussed. None of these prices reflect traditional supply and demand. They're not market prices in any normal sense. Antimatter's price is theoretical, based on production costs for something that barely exists. Endohedral fullerenes have only one manufacturer in the world. Californium-252 has 2 production facilities total. Red diamonds are so rare that each one is essentially unique. Painite was limited to 3 crystals for half a century. Moondust is mostly illegal to own. Venoms require dangerous extraction from living creatures. Radioactive isotopes decay away. Rare gemstones form through geological accidents so improbable they happen only once in specific locations. These are substances that exist at the extreme edges of rarity, complexity, and difficulty. Their prices tell us something fascinating. Value isn't just about usefulness. It's about scarcity, about the energy required to create or obtain something, and about the human desire to possess what almost nobody else can have. But let's bring this home with a thought experiment. Imagine you could choose one substance from this list. You get exactly 1 gram, legally obtained with proof of authenticity. What do you pick? The antimatter is impossible. It doesn't exist in gram quantities and would annihilate anything it touched. The endohedral fullerenes are powder worth $167 million, but who are you going to sell them to? The Californium-252 will decay in 2.6 years and is lethally radioactive. The red diamond could be sold, but it's so rare that selling it would immediately attract attention from law enforcement wondering where you got it. The painite, muscovite, grandidirite, taphite, benitoite are similar, incredibly rare gemstones with tiny markets. The moondust is probably illegal. The venoms have to be kept refrigerated and properly handled. The radioactive isotopes are dangerous. The drugs are illegal and addictive. Here's the paradox. The most expensive substances in the world are, in many ways, the most useless to an ordinary person. You can't easily sell them. You can't use them. Many of them are dangerous or illegal to possess. Their value exists in a strange space, theoretical, scientific, collectible, but divorced from everyday utility. Gold, by comparison, sits at the bottom of this list at about $164 per gram. But gold is liquid. You can sell it anywhere, anytime. It's recognized as valuable worldwide. It doesn't decay, it's not radioactive, it's not illegal. Sometimes the most expensive thing isn't the most valuable. The world's most expensive substances reveal something about human nature. We're obsessed with the rare, the difficult, the nearly impossible. We'll spend billions to create antimatter that exists for milliseconds. We'll pay millions for a red diamond smaller than your fingernail. We'll risk death to extract venom from scorpions. But here's the real question. What happens when these substances become easier to produce? If scientists crack large-scale antimatter production, does it become the fuel of interstellar travel? If we can manufacture endohedral fullerenes cheaply, does every phone get atomic clock precision? If lab-grown red diamonds become common, do they lose their mystique? If we mine helium-3 from the moon, does fusion power become viable? If painite deposits are discovered elsewhere, does its value crater? The future of value is always shifting. What's priceless today might be commonplace tomorrow. What's common today might become extinct and priceless in the future. The substances that top this list aren't just expensive. They're signposts pointing toward the future of technology, medicine, and human capability. They represent problems we're still solving, boundaries we're still pushing, and mysteries we're still unraveling. And maybe that's what makes them truly valuable.